Okay, so let's resume. Right now, any questions? Where you find anything unclear or? Yes?
Yeah, given from my knowledge, I know that there has been no acceptable proof that P is not equal to NP.
Yes.
Your proof, has it been like examined or?
It has been examined, but some says yes, this is a proof. Some says no, this is not a proof. Okay. But the ones that says this is not a proof, they have had serious errors in their arguments. Doesn't say anything about my proof, of course. And my proof is, and that's the point, is in Hilbert's proof theory. And that means that there are special rules, very simple special rules, that you can check each step. And I will come back to your question. If there is an error, there should be where I'm using Hilbert's proof theory, that means some of the proof rules or the axiom is wrong. Or there is something wrong with the proof theory, if there is an error. So that's the situation. So it would be rather easy to say this is wrong. Here is where you go wrong in your proof theory. But this is informal, but it can be transformed to a proof, a formal proof in that proof theory. But there is a little work with that. So that's where we are. Could computers do this? Computers are doing more and more what is considered intelligent. And proving theorems is considered to be an activity of intelligence. So could the computers come up with a proof like this? Within AI, there is something called theorem proving. That is that you use formal logic and you try to get the computers to prove things. And they can prove a lot. Could they prove this? Well, what theorem provers can do too is to verify. That is, they could check a proof when there is one. So this proof that I'm giving you, that is informal for practical reasons. But if I make this formal, then could a theorem prover check it? So if you take that simpler part of what theorem provers can do. So the proofs of lemma 1 and theorem 1 and theorem 2 are verified using a theorem prover. The theorem prover that I used is a resolution-based theorem prover called Vampire of Ryazanov and Voronko. Voronko was here in Uppsala some time ago. And it is up and running on a machine in Miami. So I run it on the net. So what Vampire has done is not from the proof I've done, because it has to be formalized. So I have gone through and formalized it in the first order logic, all the proofs. And those proofs have a Vampire checked. So far, so good. They have a competition on a rather regular basis. It's a word competition, word championship, almost every year. And the Vampire is one of the best theorem provers. It's kind of a word champion in theorem proving. And then I know Andre, so I asked him if I could use his Vampire. Or I asked him for advice, which theorem prover do you recommend? And he recommended Vampire. And this site in Miami has a library of problems on which people with theorem provers can check out their theorem prover for various reasons, how fast it is, if he can solve problems or things like that. And there they have a standard syntax of how you write lemma 1. Here it is. So here it says first order formula and the name, and that it is conjecture. Here it says in SAT P, that stands for that SAT is in P. If that is true, then we have the size. We are talking about resolution proofs. So here we talk about the size of the resolution proof. And here is what we are proving. And F is a tautology. And we prove the F, and then here is the size of that proof. And here is the expression in a polynomial. This T stands for a polynomial formula. So that is a bit of coding. Obviously, things could go wrong. In order to prove this lemma 1, it uses a few more corollaries than I have used. We are down to basic proving, but they are not difficult. Vampire proved them too, so let's look at what the proof becomes here. So it uses corollary 1 and 3, then there are a few other corollaries, 4 and 5. I have simplified the presentation of the proof a little bit, so this could be simplified too, but not much. So here is Vampire's proof. These are resolution steps. Refutation found. Here it says, okay, here is the proof. I found the proof. And then we can go forward and see where it started and how many lines it produced. That's a measure of the complexity of the lemma. Okay, so here's another page. And here's another one. And here's another one. Oh, here's another one. Done? Yes. So, there were a few lines of resolution code. But lemma 1 is the essential result. After that, anything else is much simpler. So this is a measure of how complicated Vampire thought the result was. Okay, here is Vampire's proof of theorem 1. That's a major result. We need Hawkins' theorem, which is this one. Okay, so then not so big. So with lemma 1 and Hawkins' result, the result is rather simple, as you would expect. And then it can prove theorem 2. Then I use theorem 1, and then I use, if P is equal to NP, then SAT is in P. Very short proof, actually. So, what remains to be proved is the corollaries to prove lemma 1. And I have run them. So I can see that there is no problem. And the major way to prove it is by induction. Induction on the computing time. And of course, from the more informal version of the proof that I showed you to transform into a formal form of Vampire. That's work too. That's why I can say that this is a proof in Hilbert's proof theory. That is, the proof can be transformed into a formal proof in Hilbert's proof theory about resolution proofs. So if there is something wrong with the proof, well, there should be the rules for proofs, which are rather simple, not many, but the rules, there should be an error there, or there is something wrong with the proof theory. I doubt the latter. We can go back to the original formula, what lemma 1 looked like. Here is lemma 1. So there, if SAT is in P, then the size of the resolution proof that exists is polynomial. I mean, this is a little more convenient than all that coding. But one of the problems here is to take all these formulas and transform them into the TP version of a Vampire. So that's one problem. Can a computer do that? Translation, and I think it essentially is correct. And that a theorem prover can do. Maybe not right now, but that's plausible. And For getting theorem provers involved in solving hard problems, that might be a step that would be pleasant to have. But I think that's doable. Okay, so what can we say? Verifying a proof like this, yes, that's within reach, I would say. Maybe for some results it's difficult to verify. It's a lot of work. But if you want to be sure, and the question is how much sure do you get after a proof of vampire? But at least you can say, well, if there is something wrong here, put your finger where it is. So verifying results like this is within reach. And maybe most people would like to have the theorem provers more convenient. But they are very impressive, I would say. It was my first exercise with vampires, so I'm not sure that my result shows how good the vampire is. But I got impressed how good it was, and fast. I just sent it over the Atlantic, and it almost started to print the result right away. So I just took one corollary after the other, and then lemma 1, and then when I had lemma 1, I put in Haken's result, and there it was. So verifying theorems, that is within reach. So what parts are difficult then to come up with the proof in the first place? Well, again, we have to concentrate on lemma 1, since that gives the proof, because then we can take Haken's result. And it is about resolution proofs. When we run this program that we call axiom B, and we have the goal, a tautology, when we run that in first-order logic and construct propositional formulas, that's the idea. We are not constructing anything different. It's just an instantiation, and we pick up the instantiated formulas of the axiom. Nothing else happens. Well, could a computer come up with that idea? Yeah, why not? And then what is involved? Well, it's off-the-shelf math. The proof method is essentially Hilbert's proof theory, and it's available in textbooks. For example, Kleeni's mathematical logic. So a theorem prover should be able to do that. So what remains is the axiom. Could a theorem prover axiomatize Turing's theory? Yes, why not? But that I think we have to wait for. That's where I should put my finger, where there could take a while. Well, there are intelligent activities going on where I don't think computers are quite ready. And proving theorems like this one, for example, is too difficult, I would say, at the moment. But there are not many steps in the proof. Maybe it's just to come up with the axiom. But maybe the axiomatization is a part where a computer could have difficulties. I'm not aware of where computers have been axiomatizing theories. Okay, so that's AI and theorem proving. Hilbert, I'm using his proof theory. He axiomatized arithmetic. And he suggested that mathematics should be done that way, that you axiomatize it, and then you prove that from your axiom, you prove that you cannot prove a sentence and its negation, that is, that the theory is consistent. Unfortunately, that was not doable. Gödel came up with a famous theorem for the theory of arithmetic that Hilbert had axiomatized. When I have axiomatized Turing's theory here, do I have that problem here? Do I have to assume that this theory B is consistent because after all, I'm using it. And if it's not consistent, I can prove both that P is not equal to NP, and can also prove that P is equal to NP. What the proof is, okay. Well, not quite, because remember, I have this set U of deterministic Turing machines that are computing whether a formula is satisfiable. And in this subset of computing, the theory is all right. That subset cannot go wrong. And I'm just assuming that one of them can do its work in a polynomial computing time. So I'm safe in that subset of computing. Otherwise, I would assume that B is consistent. And then the result wouldn't be as nice. That if B is consistent, then P is not equal to NP. That's not the same as P is not equal to NP. Do you prefer vampire's proof or this human-oriented version?
Human version.
You prefer that one? But would you trust it without vampire's backup? There are people that don't trust it, but they have never come up with an argument that doesn't have an error. That's at least what you can ask for. If you have an argument, don't have errors in it.
What kind of arguments what do they say?
One argument was that this B, you can prove in this theory B from axiom, you can prove two strong things. So it's useless. So what the results you have got here are useless. This B is too strong. And that is not so good, because the entire theory of computing is this axiom. And that's where complexity is defined. Then, if the formal version is wrong of how you define complexity, then all these informal results must go the same way. Of course. They cannot be right if the formal version is wrong. So that's an error. And then arguments that there is a transformation here, that you have to assume that you are doing transformation, so you are introducing another assumption in your argument. And clearly you are not. The only assumption is that set is in P. No other assumption is used. You can check that by the rules. That's why Hilbert's proof theory is strong. You have to make explicit what you're assuming. This idea of axiomatizing your theory and make that explicit, that was Hilbert's idea, because the idea of having axioms goes back to Euclid, and people proved results in geometry, but they introduced more than the informal axioms of Euclid. And what Hilbert's program was about, make the assumptions explicit. And the only assumption what is introduced here is that set is in P. Because if we have set in P, we have this directly from the definition here of set is in P. So we get that. So we get the axiom B, and we have the F that we should prove, and it says that you can only compute the proof in polynomial computing time. Okay then, so let's do that. So then we start to do that, and we follow the rules, and they are Robinson resolution proofs, just that we instantiate the axiom. And the formulas are the blue ones here. All that are the instantiated formulas. So then if we collect them, here they are. It's very clear that they are Robinson resolution proofs without any transformation at all and without any extra assumption. So that's one argument. Another error. Well, then there was one argument that, okay, Hawkins' result is about pigeonhole formulas, and there are Turing machines that can check whether these pigeonhole formulas are valid or not. in polynomial computing time. But that's a non-deterministic Turing machine that can do that. And here we are talking about deterministic, and they're quite different. So that's another error. And then there are arguments that there are different proofs. In Hawkins' result, if you look at Hawkins' result, here, Hawkins' theorem, it says that it's not the case that there exists a polynomial Robinson resolution proof for all sufficiently large tautologies F. And here I said if we assume SAT, then we have that. This result, if you assume SAT, you have a polynomial Robinson resolution proof of F. And since you have a proof of F, you know that F is a tautology. Resolution only proves valid formulas. And Hawkins' result is for all sufficiently large valid formulas. So you can apply Hawkins' result. So that's another error. Okay? Is there any other question or remark? Yes?
Are there any known researchers that are still trying to prove that P is equal to NP, or have everything given up?
I don't know what people are doing. Usually they only show the results when the results are delivered. But I think there are people working on it. I think so. Sure. And the opinion before a proof, whether P is equal to NP or not, they say that most people think P is not equal to NP. Believing and proving it, there are different things. Of course, it's useful to have intuition, I'm sure. But to settle the thing, you don't settle the question without a proof. But there are people that think that P is equal to NP. Or at least think it's a possibility. Before P is not equal to NP is proved. Or the other way around, of course. Okay, so thank you very much.